When we think of heat, different images come to mind. We may think of a fire blazing on a cold winter day, or the hot lava erupting from a volcano. We might associate heat with temperature, like the temperature of water from a faucet, or the number of degrees marked by the rising alcohol in a thermometer. And we might think of heat in terms of energy, such as energy from a hot burner that fries an egg, or the enormous energy of the sun, the ultimate source of almost all the energy on Earth. This program is about heat, temperature, and energy. It is about how these three things are related, but also different.
All matter on Earth contains energy. There is energy in the gases of the Earth's atmosphere and the water that forms its oceans. There is energy in the steel and concrete of a bridge, and even in grains of salt. All matter contains energy because of how matter is put together. Matter is made up of much smaller, invisible particles, atoms and molecules. The smallest particle of salt, for example, is a molecule consisting of a single sodium atom linked to a single chloride atom. This is why the chemical name for salt is sodium chloride. In a grain of salt, these molecules are bunched tightly together and hold each other firmly in place, forming a regular pattern. But even in something solid like salt, molecules are in constant motion, vibrating back and forth. This internal energy, or energy inside matter, is called thermal energy.
Even something as cold as ice has thermal energy. The water molecules that make up ice vibrate somewhat. But the water molecules in a glass of warm water move around many times more rapidly and have much more thermal energy. When you put ice into warm water, the water gives up some of its thermal energy to the ice. The flow of thermal energy from one place to another is called heat. Heat always flows from something warmer to something colder. When heat is added to a substance, its molecules move faster. When heat is taken away, the molecules slow down.
Heat energy can be converted into other forms of energy, and other forms of energy can be converted into heat energy. In a power plant, heat can turn water into steam that turns turbines. The mechanical energy of turbines, in turn, can be converted to electrical energy. And electrical energy can be converted to heat, as when the coils on this electric burner get red hot. Another illustration of how different forms of energy can be converted to heat energy is provided by this pad, which contains special heat-sensitive chemicals that change color. When you put your hand on the pad, it leaves a slight impression caused by the heat in your skin. If you then rub your hands together vigorously, this mechanical energy causes friction that excites the molecules in your skin, making your hands hotter. And if you place a hand on the pad again, it will leave a much brighter impression.
In addition to making their molecules get more excited, Adding heat causes most substances to change in other ways. A simple experiment shows how. This metal ball was designed so that it just fits through this ring. But observe what happens when this student heats the ball. Any experiment involving fire should be done under the supervision of a teacher or other adult. After the ball is heated, it no longer fits because the excited molecules in the ball have moved farther apart, causing it to expand. Now look at what happens when she puts the ball into some cold water to cool it off. When most substances lose heat, they contract because their molecules are less excited and move closer together. Builders and engineers have to take into account that steel, concrete, and other building materials expand when heated and contract when they lose heat. Bridges, for example, have expansion joints that give the steel and concrete sections room to expand in the hot summer months. Water is an important exception to how substances expand and contract when heated and cooled. When water freezes and becomes solid ice, it expands rather than contracts because of a special way water molecules and ice bond to each other.
As they become hotter or cooler, gases and most liquids other than water expand and contract much more than solids. The base of this thermometer contains liquid alcohol. When this liquid is heated by putting it into hot water, its molecules become more excited and move farther apart. The alcohol expands and rises up a very thin tube that runs the length of the thermometer. When it is cooled, the alcohol contracts as its molecules become less active. As it contracts, the alcohol falls down the tube. A scale along the tube marks the temperature. Some thermometers use the Celsius scale, which is based on the fact that water always boils and freezes at the same temperatures when the pressure in the atmosphere is the same. At sea level pressure, 100 degrees Celsius marks the boiling point of water, and 0 degrees Celsius marks the temperature at which water freezes. Other thermometers use a different scale. With a Fahrenheit thermometer, the freezing point of water is 32 degrees Fahrenheit, and the boiling point is 212 degrees. The numbers of the two scales are different, but the temperatures they mark are the same.
No matter what kind of scale it has, a thermometer measures temperature, not heat. Temperature and heat are different in important ways. Temperature is a measure of how fast the molecules in a substance are, on average, moving. Measure the temperature in a tub of warm water. Then fill a cup with water from the tub and measure the temperature of this water. The two temperatures will be the same. This is because the molecules of water in the cup are moving around, on average, as much as the molecules of water in the tub. But the tub has much more thermal energy because it has many times the number of water molecules as the cup does. Because it has so much more thermal energy, more heat can flow from the water in the tub than the water in the cup. The water in the tub, for instance, could quickly melt a pitcher of ice.
Which do you think has a higher temperature? The flame of a candle or a radiator? Which has more heat? If you wish, You may stop the video now to discuss these questions. Otherwise, the program will resume in 10 seconds. The flame of a candle and a radiator show the differences between heat and temperature. The flame has a much higher temperature, but the radiator has much more thermal energy because it has more molecules than the flame. It can give off a great deal more heat, enough heat, in fact, to warm a whole room. While temperature is measured in degrees, heat is measured in units called calories. A calorie is the amount of heat it takes to raise the temperature of 1 gram of water 1 degree Celsius. The value of any kind of fuel can be measured by how much heat it gives off when it is burned. A gram of gasoline gives off about 11,500 calories. A gram of soft coal gives off 6,000 calories. And a gram of oak gives off 4,000 calories.
We saw earlier that heat always flows from something hotter to something colder. There are different ways that this happens. An experiment shows one way that heat is transferred from one place to another. Here, a student puts some wax on the heads of 3 tacks. He then sticks the tacks so that they are spaced evenly apart along a steel rod. A Bunsen burner then heats the end of the rod. In a few minutes, the heat from the burner is transferred from one end of the rod to the other. The wax melts and the tacks fall off, one after the other. But how does this happen? The steel rod is a solid. The molecules that make up the end of the rod vibrate more quickly when heated. But the molecules can't move from one end of the rod to the other.
Poole provides a hint about what happens with the molecules of the rod. When someone makes a shot, energy is transferred from the player's arm to the white cue ball. When the cue ball hits a second ball, it transfers its energy to the other ball. Often the cue ball hits one ball that in turn transfers energy to still another ball. Something similar happens with the molecules that make up the steel rod. As the molecules at one end are heated, they speed up and vibrate more. These molecules transfer energy to the molecules which become excited and move more rapidly. These molecules in turn excite the molecules next to them, and so on. In this way, heat energy is passed on from molecule to molecule the whole length of the rod. This type of transfer of heat is called conduction. Conduction occurs when heat energy flows from one molecule to another as they collide.
Different substances do not conduct heat equally well. These spokes are made of different kinds of metal, including copper, aluminum, steel, and iron. Here, a student has attached a tack to the end of each spoke. He then heats the hub so that each spoke gets an equal amount of heat. The experiment shows that the wax melts and the tack falls off the copper spoke before any of the others. The next tack to fall is from the aluminum spoke, because aluminum is the other metals except for copper.
In general, Metals like copper, aluminum, and steel are all good conductors. Here, heat from the burner is easily conducted by the metal pot to the sauce. However, some other substances like wood are not good conductors. Many pots have wooden handles because wood does not conduct heat well from the pot to one's hand. Poor conductors like wood are known as insulators. Plastic is also an insulator. This plastic cup helps keep tea warm because the heat from the tea doesn't conduct easily through the plastic to the colder air around the cup.
Here is a question to think about or discuss. How do materials that are good insulators cut down on the amount of energy it takes to heat a home? You may stop the video now. Otherwise, the program will resume in 10 seconds. Insulators are used to help conserve heat in houses and save energy. This insulation is made of fiberglass, which conducts heat poorly. In an attic, it helps prevent heat from escaping through the roof. Certain kinds of windows also help conserve heat. This cutaway model shows how some windows have a layer of air between two layers of glass. Air and other gases are poor conductors. The molecules that make up a gas are far apart, making it hard to transfer energy from one molecule to another.
Liquids are also poor conductors because their molecules are farther apart than the molecules that make up a solid. But heat in liquids and gases can be transferred through another process, convection. Convection is the flow of energy that occurs in a gas or liquid. You can see convection in a pot of heated water. As the water gets warmer, it expands in the bottom of the pot, is less dense, and rises. As the warmer water rises, it cools, becomes more dense, and sinks again. Convection heats homes. A radiator, for example, warms the air near it. This air rises because its molecules are farther apart and it is less dense. The warm air cools as it moves through the house. As it cools, it sinks and moves back to the radiator and is warmed again. Convection occurs in the air in the Earth's atmosphere and makes it possible for these hang gliders to fly. As the sun beats down on the land and bare rock, heat is reflected and warms the air above. This warm air rises, providing strong thermals or updrafts that keep the gliders aloft. Heat from the sun also causes huge convection currents in the Earth's atmosphere that are responsible for weather patterns and wind.
The sun is the ultimate source of most of the heat energy on Earth. At its surface, the sun's temperature is about 10,000 degrees Fahrenheit, or about 6,000 degrees Celsius. But separating the sun from Earth are about 93 million miles, or 150 million kilometers, of mostly empty space. In space, there are not enough molecules to transfer heat by conduction. There also are no gases or liquids in space that can transfer heat to the Earth by convection. But there is a third way that heat can flow from one place to another, even through empty space: by radiation. Radiation can pass through space as waves of energy that are similar to waves that transmit radio and television signals. When radiation from the sun hits things on Earth, it excites molecules and makes them vibrate faster. This is what makes one's skin feel warm on a sunny day. The heat felt from a fire is also transferred by means of radiation. In fact, all heated bodies, whether the sun, a fire, a light, or an electric toaster, radiate heat.
An experiment shows that heat from radiation has different effects on different kinds of surfaces. Get 2 identical cans and wrap black paper around one and white paper around the other. Fill each can to the same height with water. Place a piece of cardboard on top. Then leave both cans in sunlight, so that each is equally exposed to the sun. 15 minutes later, come back and measure the temperature of the water inside the white can. Then compare it to the temperature inside the black can. The water inside the black can gets hotter because dark surfaces absorb radiation better than light surfaces. That is why people wear dark clothes in the winter when they want to be warmer, and wear light-colored clothing during the summer when they want to absorb less heat.
In this program, we saw that matter is made up of atoms and molecules. Even in something solid, these molecules are constantly moving. The energy associated with this movement of molecules is called thermal energy. Heat is the movement of this energy from one place to another. Heat always moves from something warmer to something cooler.
We saw that when heat is added to most substances, they expand as their molecules pull farther apart and take up more space. When most substances are cooled, their molecules move closer together, and they contract.
We saw that thermometers measure temperature, but that temperature is not the same thing as heat. The flame of a candle, for example, has a higher temperature than a radiator, but the radiator can give off more heat.
We saw that heat is transferred from one place to another in different ways. Heat can be transferred through conduction when vibrating molecules collide with other molecules and pass on their energy. Some materials, like metal, are good conductors. Things that are poor conductors are called insulators.
Heat can also be transferred in liquids and gases through convection. A liquid or gas expands and rises when it is heated and sinks as it is cooled. Convection currents in the atmosphere are responsible for wind and much of our weather patterns.
Finally, we saw that heat can be transferred even through empty space by radiation, and that radiation from the sun is the Earth's most important source of heat.
episode of Hot Treats with your hostess, Vivian Cupcake.
Oh, why, hello there. I'm ever so glad you could join me today, because the kitchen is such a wonderful place to learn about heat. Today we're going to cook with this metal baking pan and this glass baking pan. Say we pour half our brownie batter into this metal baking pan. This will be chocolatey and delicious.
Careful.
Mix it out. The tasty batter will turn into scrumptious brownies when heat from the heating element heats up the metal pan, and the metal pan transfers its heat to the brownies. That's heat conduction. Conduction heats the glass baking dish too. But because the glass is clear, red light and infrared light, that's heat, passes right through the glass baking dish to heat the brownies. That's heat radiation. The metal pan isn't clear, so it reflects the infrared light. Heat radiation cannot heat up the brownies in the metal pan. That's why we cook our brownies for a longer time when we use a metal pan.
You want to, watch it. Careful now.
And this is my favorite part of studying heat. Oh, that is hot.
This has been another edition of Hot Treats with Vivian Cupcake.